Hello everyone, we're going to go ahead and get some extra practice using sigma notation and summation formulas. Let's rewrite, using summation formulas, this sequence given by the summation from I equals 1 to n of 6i times I minus 1 over n cubed. Our goal is to use summation formulas to rewrite this summation without the sigma notation. Then we're going to evaluate that formula, call it S of n, for an upper bound of 10, 100, 1,000, and as n approaches infinity. Rewrite the summation without the sigma notation, without the summation notation, and then evaluate it as n approaches 100, 10, 100, 1,000, and as n goes to infinity. So let's first begin by rewriting this. We've got the summation from I equals 1 to n, 6i times I minus 1 over n. I'm going to first begin by factoring out constants. Obviously, 6 is a constant. N cubed is actually a constant too. N represents the upper bound of our summation. It can take on values like 10, or 100, or 1,000. Say I want to evaluate for n equals 10. What's the summation from I equals 1 to 10? This n cubed right here would therefore be 10 cubed, just a constant. Say the upper bound is 100, like in this exact example. What's the summation from I equals 1 to 100? Well, this n to the third would be 100 cubed, also a constant. 6 is a constant, so is n cubed, so we're going to factor them both out. Let's simplify I times quantity I minus 1. I times I is I squared. I times 1 would be I. Bring down 6 over n cubed times the summation. I equals 1 to n of I squared minus the summation. I equals 1 to n of I. I'm going to replace the summation of I squared and the summation of I with the correct summation formulas. The summation of I squared would be n times n plus 1 times 2n plus 1 over 6 minus the summation from I equals 1 to n of I. In terms of n, that would be n times n plus 1, 2. All right, let's start expanding these parts of our formula here so far. 6 over n cubed still out in front. N times n plus 1 would be n squared plus n times 2n plus 1 still over 6 minus n squared plus 1 n squared plus n over 2. Let's keep expanding n squared plus n times 2n plus 1. N squared times 2n would be 2n to the third. N squared times 1 is n squared. N times 2n is 2n squared. N squared plus 2n squared is 3n squared. One times n is n. I want these to have common denominators. This has a denominator of 2, this has a denominator of 6, so I'm going to triple the top and bottom, multiply the top and bottom each by 3, so minus 3n squared plus 3n over 6. 6 over n cubed down 2n cubed. 3n squared minus 3n squared cancels out. 1n minus 3n is negative 2n. 6. Now I can multiply this expression times 6 over n cubed, what I factor out in front first. 6's cancel out. Leaves me 2n cubed minus 2n over n cubed. I can divide everything by a factor of n. 2n cubed, 2n, and n cubed all share a common factor of n. So 2n squared minus 2 over n squared. Here's our summation formula in terms of n, or our given summation that we started with. Using summation formulas, I took this sigma notation, I wrote it as a formula in terms of n. Now we're going to evaluate S of n for n equals 10, 100, 1,000, and as n approaches infinity. S of 10, S of 100, S of 1,000, and then the limit, as n approaches infinity, of our summation formula, 2n squared minus 2 over n squared. This needs to be 1,000. Forgot an extra 0 here. Go. All right, S of 10. Replace n with 10. 2 times 10 squared minus 2 over 10 squared. That's 2 times 100 minus 2. 2 times 100 is 200 minus 2, which is 198, divided by 10 squared, which is 100. 198 divided by 100 is 1.98. Do the same thing for 100. 2 times 100 squared minus 2 over 100 squared. 2 times 100 squared, that'd be 2 times 10,000 or 20,000. 20,000 minus 2 is 19,198 divided by 100 squared. That's the 10,000 again. $19,998 divided by 10,000 is 1.9998. Let's do the same thing for 1,000. Our summation formula, let n be the same as 1,000. 2 times 1,000 squared minus 2 divided by 1,000 squared. Let's see, 2 times 1,000 squared. Would be 2 million minus 2. 1,999,998 divided by 1,000 squared. That's that same 1 million again. By dividing those, 1.999998. Now what's the limit of our summation formula as n approaches infinity? You can obviously, based off of the work so far, as I increased n, as I went from 10, 100, 1,000, my summation got pretty close to 2. Let's prove that using limits. As I increase n, as n tends toward infinity, this summation should tend towards 2. Let's see, 2n squared minus 2 over n squared. I'm going to break that apart and divide each of these by n squared. Two n squared divided by n squared minus 2 over n squared. N squareds cancel out, looking at the limit as n approaches infinity. 2 minus 2 over n squared. Take the limit of each of these terms one at a time. As n approaches infinity, the limit of 2 should still be 2. This term is independent of n. It's constant. There are no n's in it. So regardless of what n does, this 2 stays 2. Over the next term, as n goes to infinity, 2 over n squared, 2 divided by a very large number as n tends towards infinity. Any constant divided by a very, very large number gets closer to 0 pretty quickly. This would be 2 minus 0, just 2. Some good work at remembering limits, as well as evaluating sigma notation using summation formulas for different upper bound values, and seeing how these sums behave for n approaching infinity, as n varied from 10, 100, 1,000, and eventually going to infinity. We'll call that there and start working on Riemann sums starting next time.